Hello everyone, I'm Andy.
I'm Corwin.
And I'm Kiran, and we're Team 1124. This is a presentation of our solution to the SCUDEM 2025 Problem A, raining cosmic space dust.
Our task for this problem was to predict how the mass and velocities of cosmic dust with different entrance sizes and velocities changes as it falls towards the Earth as a result of atmospheric conditions. Following from this task, we should work backwards to predict the distributions of the masses and velocities of cosmic dust particles when they first enter the atmosphere using given information on the final mass and time period.
Part 1, Assumptions. We first need to declare some conceptual simplifications. First, we assume that the cosmic dust is uniformly one material. This allows us to assume uniform density and that other material properties are uniform throughout the cosmic dust. Second, to reduce the problem to a better known problem for research and model application, we've assumed that cosmic dust will have the same physics falling through the atmosphere as a micrometeoroid, because of their similar size with cosmic dust, measuring less than 100 nanometers and micrometeoroids measuring between 10 nanometers and 2 millimeters. This allows us to use existing models for micrometeoroids for cosmic dust. Third, we've assumed cosmic dust is a perfectly spherical shape and does not experience fragmentation, even as it burns up. This assists us with finding cross-sectional area and cosmic radius as part of some of our differential equations and variables. Fourth, for this model, we will only use the velocity downwards, as it is the only velocity that affects the height. Following this, we will not consider where on Earth the cosmic dust lands, thus we've assumed that it must land on sea level. Finally, for the second task of predicting backwards, we've assumed that the Earth's atmosphere has not changed significantly between the time periods we're predicting for. This allows us to assume that we don't need to adjust any coefficients in our model to do the backwards prediction task. As for different variables' assumed values, we've assumed density equals 2 grams per centimeters cubed. This follows from our assumption of uniform material. This has an additional benefit of allowing us to easily interchange between calculating with size and mass for different equations. We've also assumed that heat of ablation and the drag coefficient are constant, using values 6.5 times 10 to the power of 6 joules per kilogram and 1.5 respectively, taken from sources studying the same dynamics. Heat of ablation being constant follows from the entire object being the same material, and thus having the same material properties. Drag coefficient being constant allows us to avoid unnecessary complexity caused by the vaporizing molecules that increase drag coefficient. As for the heat transfer coefficient, we found a function that utilizes values we already utilize within our model. We assume that the heat transfer coefficient is accurately estimated by 2.26 over square root Reynolds number, where Reynolds number is the initial atmospheric density times the entry velocity times the body radius over the dynamic viscosity of air. We have all values except for the dynamic viscosity of air, which we've assumed to be 1.18 times 10 to the power of negative 5, as given by an article. Our starting height is assumed to be 1,000 kilometers. We found that the beginning of the exosphere is a blurry line somewhere between 600 kilometers and 10,000 kilometers. We've thus assumed that 1,000 kilometers is our starting height. Since our value of atmospheric density is a function that's input values end at 1,000 kilometers, we've assumed that the space-like conditions further up will not have any significant effect on the mass and velocity of the cosmic dust. We've assumed that the atmospheric density can be accurately estimated by the NRML-MSISE00 model, a global reference atmospheric model providing a wide range of data allowing us to model atmospheric density as a function of height. Finally, we've assumed that gravity is a function of height, given by the equation shown, where g0 is gravity at sea level, which is negative 9.81 meters per second squared, and RE is the average radius of the Earth.
Part 2, the model. Our first differential equation relates mass loss over time to C, which is the heat of ablation in joules per kilogram, the heat transfer coefficient, atmospheric density, surface area, and velocity. The mass loss occurs due to drag, which produces heat. Our second differential equation relates the change in velocity to gravity, mass, and drag force. This equation comes from analyzing the vertical forces acting on the particle. We also have the derivative of altitude with respect to time as velocity, which we use to compute altitude at a given point. Note that we can rewrite surface area as a function of mass by using our assumptions about constant density and the particle's spherical shape. Because our set of differential equations does not have an analytical solution, we use the Euler-Kromer method to update our mass and velocity at each step. We used a time step of dt equals 0.001, and each simulation took around 800 seconds, so we had roughly 800,000 steps for each test. At each step, we also updated our air density, gravity, and area variables.
Part 3, Simulations. We created a model that took initial mass and initial velocity and output a calculation for the final mass based on our differential equations. We recorded the final mass when the altitude was 0 or when the particle landed. And if our mass was negative at any point, we returned 0 to signal that the particle had completely burned up. We noticed that for the initial velocity, initial mass pairs that didn't completely burn up, there was a time when speed and mass would rapidly decrease. This happens when v cubed surpasses 1 over c, which is when the time derivative of mass becomes negative. And as mass decreases, the drag coefficient blows up, so speed also decreases. This creates a positive feedback loop until the point where the magnitude of velocity gets small enough that dm dt goes to 0 and we reach equilibrium, as we see here in the graphs where time equals 100 seconds. We iteratively ran our model over a range of initial masses ranging from 1 gram to 0.1 grams, and initial velocity ranging from 4 kilometers per second to 14 kilometers per second downwards. We found that particles moving faster than around 12.5 kilometers per second all completely burned up. And we also found that the greater the initial velocity, the less effect initial mass had. We need to find the distribution of cosmic dust, so we took a contour of our final mass versus initial conditions surface from our previous slide. We applied the Laplace likelihood function to introduce uncertainty to our model. It assigns higher likelihood to initial conditions that get closer to the desired final mass, which is perfect for our data since it has heavy tails for high magnitudes of velocity and it's also not normally distributed. We plotted our surface with initial velocity, initial mass, and likelihood axes. To account for the strata and time periods specified by the problem, we looked at the mass loss of the particle, which is an exponential function of time. We used mass loss per year values to find the mass of the particle when it first landed. In our first graph on the left, we found that the overall mass in conditions similar to Antarctica would decrease around over 60% over a million years. So when we are trying to work backwards on a particle with mass 10 to the negative 5 kilograms on the surface, we would find that the mass when landing was around 1.7 times larger. And when we account for that, we get a slightly different graph from the last slide. In our second graph, we found that the overall mass in conditions similar to a desert would almost completely reduce the mass of a particle. So finding a particle with mass 10 to the negative 5 kilograms on the surface would imply that the mass was hundreds of times larger. And when we account for that, our graph suggests that such a large particle could have only landed under extreme conditions with the maximal possible entry mass and lowest possible entry velocity, which is why our graph looks like that.
Part 4, closing. We could extend our solutions to this problem by accounting for a few things. For example, we found that many articles discussing the falling of micrometeoroids often use a function of photometric mass loss or brightness as a parameter for heat of ablation. Furthermore, we could make the heat transfer coefficient a function of kinetic energy, and thus as a function of velocity. This would add a complexity that we have considered. Finally, by allowing the cosmic dust to be any shape, the drag coefficient would need to account for the rotations of the cosmic dust, and the mass loss would change the shape, ushering in the question of what parts of the cosmic dust would lose mass first.
Here are our references. Thank you for watching.